Boom. All right, so we're continuing our discussion of some of the introductory ideas, some of the introductory concepts where this whole thing of differentiation is concerned. So what we're going to do here, we actually taking a little section of this curve, the section from here to here, and we exaggerate it here, we blow it up, we zoom in, so to speak, so that we can see the thing even clearer, right? Because what we're going to do now is shorten the line segment even further, right? We already established that the gradient is decreasing. But the next question we want to ask is, how far is it decreasing? Is there any point when it will stop decreasing? In other words, and listen to me carefully now, is there any limit to this progressive decline, if you want to say that, to this progressive decrease in the gradient between this point all the way to this point here? Well, let me see. We already established that as the line segment gets shorter, it will get short to the point where it actually becomes a point. So the point is the limit of the line segment as the line segment gets shorter. So from a point of view of reasoning, from a point of view of deduction, we could deduce, even before we put the marker on the whiteboard, that any limit to the progressive decline in the gradient should also occur at the point where the limit of the length of the line segment is arrived at. Well, let me see. Let me see. That making sense, not so? Right. So we established already that the gradient between the point 24 and the point 11 is 3. Let me take another point. So let me take the point, let me say 1.75. Let me say 1.75, this will be 1.5. 1.5 should be somewhere here. 1.75 should be somewhere here. 1.25 should be somewhere here. And then we could go to, let me say, 1.1. And then we could go to 1.05. All right? So we make the line segment progressively shorter. And let me see what happens to the gradient. Right? So at x equal 1.75, y will be 1.75 squared. Well, let me see that. So let me see what that is now. All right? We could get an exact value because 1.75 squared would be 1.75 squared is equal to 3.0625. Well, look at that. So this is the point 1.75. Need some more space here. 1.75, 3.0625. Right? And what's this point here? 1.5. The square of 1.5 is 2.25. 1.5, 2.25. This point here is 1.25. What's the square of 1.25? 1.25 squared is equal to 1.5625. So this here is the point 1.25, 1.5625. Make a proper 5, right? This here is the point. Let me see what this point is now. Right? This is the point we had discussed this as 1.1. Let me say 1.1. 1.1 squared is 1.21. So 1.1, comma 1.21, and this is the point 1.05. 1.05, comma 1.05 squared is equal to 1.1025. 1.1025. All right. And this here is the 0.11. Right. So we see what happening here, right? So we have all the points that we're going to use to calculate the gradient. So the gradient between this point and the point 1, 1 would be. Let me say M1 is equal to 3.0625 minus 1.5625 all over 1.75 minus 1. 1.75 minus 1 is equal to. I'm just working out everything in 1, right? Just in the inches of space. 3.0625 minus 1.5625 divided by 1.75 minus 1 is equal to 2. Okay. Yeah, I think the gradient between this, okay, so the gradient here is 2, right? Let me go again. M2 is equal to this and this. So that will be, no. What madness I do here? This is supposed to be, what craziness I do here, man? 3 point divided by 1. Oh, come now, man. Jeez and ages. That'll be minus 1. That'll be 2.0625 divided by 0.75 equal 2.75. So the gradient here is 2.75. Right. Now we take this point here. M2 will be 2.25 minus 1 over 1.5 minus 1. That's equal to what? 1.25 divided by 0.5 is equal to 2.5. The gradient is 2.5. Let me say M3 is equal to, that'll be this guy here, right? 1.5625 minus 1 over 1.25 minus 1, and that's equal to 0.5625 divided by 0.25 equal 2.25. 2.25. So we see the gradient getting smaller. Should we keep some space here? Let me see if we could squeeze up on this side. All right. Come in here now. M4 is equal to, we're dealing with this guy here now. 1.21 minus 1 over 1.1 minus 1 is equal to 0.21 over 0.1. 0.21 divided by 0.1 equal 2.1. Equal 2.1. Let me take this guy here now. M5 is equal to 1.1025 minus 1 over 1.05 minus 1, and that is equal to 0.1025 divided by 0.05. That's equal to 2.05. Only see the part, only see what happening here. 2.05. And let me squeeze in one more point just for the sake of argument now. Let me squeeze in the point 1.01. Now, let me make it even smaller, 1.001. Ha! So 1.001, that is as close to this point as we could get in terms of our own imagination. All right? 1.001, comma, that is 1 over 1,000, 1 and 1 over 1,000. 1.001 squared is equal to 1.002001. 1.002 0, 0, 1. So we have to steal some space on this side. 2, 0, 0, 1.00, 2, 0, 0, 1. Okay, beautiful. So, let me work on the gradient now. So M6, woohoo! I don't think we need this again, man. We deal with this already. So here what? Let me rub off the board and steal some space on this side. Again, let me try and preserve the actual curve itself because we might need it still. So M6 is equal to what? 1.002001 minus 1 all over 1.001 minus 1. And that's equal to what? 0.002001 divided by 0.001 is equal to, look at it, 2.001. All right. So 2.001. So you see, from here to here, the gradient moved from 6, 5, 4, 3. And then from here to here now, which is what we're dealing with here. This little region of the curve here. All right? This segment of the curve here is what we're dealing with. All right? We took in some more points in there. So in other words, we start with the line segment from here. So in other words, this point, this end of the line segment remains fixed. We start with it here, and then we bring the other end here, and then we bring it here, and then we bring it here. And then within this last gap between 2 and 1, we start to move the point progressively closer to 1. So as close as we could get in our imagination, we put it 1,000th of a unit away from 1. That is how close the 2 points are. And you move it closer, and you move it closer, and you move it closer, until it gets so close that the other end of the line segment actually converges with the original end that remained fixed. So the 2 points now converge into 1. All right? And at that point, we have what we refer to in maths as our good friend, the tangent. All right? Now, I would have spent a lot of time, well, not a lot, but a considerable time explaining what a tangent is on the mathematics side of things, where we discuss the properties of a circle. All right? And for those of you who are watching this with a view to CSEC Maths, you take the full AdMaths website and you have free automatic access to the full Maths website as well. So you get 2 for 1 if you do the AdMaths. All right? Nice. So we have our tangent, or our point of tangency, which in this case is the point 1, 1, where the other end of the line segment now actually coincides. So in other words, the movable end of the line segment, as we shorten the line segment, coincides with the fixed end. So the 2 points now converge into 1. So you no longer have a line segment in the practical definition of what a line segment is. What you have is a point. In the technical, mathematical definition, you do in fact have a line segment. You just have a line segment where the length is equal to 0. That is all. That is all. All right? And just for the sake of argument, I'm going to demonstrate again what that means. If you have a line, and you make this line progressively shorter, all right? Now, with the straight line, the gradient wouldn't change, but as they make the line shorter on the curve, the gradient changes, and we see that. So as the line segment gets progressively shorter, we see a certain pattern in terms of the movement of the gradient. All right? And then it will get so short that it actually coincides with the other point, and we just have a point here. This is your point of tangency. Point of tangency, right? And if we extend the line segment, what we in fact have is our tangent. All right? So the extension of our line segment of length 0 is what we refer to as a tangent. Look at that. You get it nice. Right? This is the extreme case of what happens between a chord and a secant line. Again, we're getting technical here. This line is a chord because it joins 2 points on the curve, but it doesn't cut the curve. If we extend the line in blue, that is what we refer to as a secant line. Yes, I went online to brush up on the definitions, okay? I'm not pretending that I had all the information in my head, right? In the course of thinking about it, I realized, but wait, we had to define certain things. We had to make it clear. We had to clarify it. And yes, I went online for some help. So if I, as a person explaining, could go for help, then you had to go for help too if you need it. You either come by me or you go by somebody else, or you go somewhere else, or you go online or whatever it is, trying to get the help. It is my hope that what this little talk we're doing here is of benefit, right? And after we go into this general talk, we will get into the actual applications of the differentiation, the questions and the differentials and all the different types of differentiation. But as I like to do as often as I can, we like to talk a little bit about the topic before we start. There will be times when I'll just drop something and say, yes, perhaps you had to take that and run with it, because the understanding of that might be beyond what you're doing now. But whenever we could, we break it down, we tear it apart, we flesh it out, we put it back together, we repeat it, and so on, so that you go into the calculation with a certain level of appreciation, a certain level of comprehension of the thing. That will help. One, it will help you to enjoy it. Two, it will help you to remember it. And it will also help you in the execution of whatever it is you need to execute. Nice? So, if we extend, I need all the markers here, man. This line in green is a chord. Remember, same idea from a circle, right? A circle is also a type of curve, right? This line, that's a line in green, is a chord. The minute we extend it past the actual curve, it actually now cuts the curve, and we refer to it now becomes a secant line. There's a secant and a chord. A chord doesn't cut the curve, but a secant line, a secant cuts the curve. Right? Same thing in red here. This red line, as it stands here, is a chord. From one point on the curve to another point on the curve. As soon as you do that, it now morphs, it now evolves from a secant line into from a chord into a secant. And the same thing happens with the black line here, chord to secant. Right? Now, so in other words, the gradient of the chord will be equal to the gradient of the secant, because the secant is just the extension of the chord. So the chord between these 2 points is an extension, is a line segment. The chord between the point 1, 1 and the point 5, 25 is a line segment on the overall secant line that passes through those 2 points. And the same argument goes for all the other pairs of points. 1, 1 and 4, 16. 1, 1 and 3, 9. 1, 1 and 2, 4. What's the importance of all of that? The importance of all of that, as we just said about 10 minutes ago or 5 minutes ago, when we actually get to the point where the length of the line segment is equal to 0, which means that the length of the chord is equal to 0. If we extend this chord of 0 length, that basically is the secant line. But because this is the secant line of a chord of length 0, we had to give it a special name. We had to call it a secant. This is what we refer to as the tangents. Right? Yeah. So we're taking my time and go through it so that they get some level of appreciation for the thing. Yeah? All right, what else? Point of tangency. The line passing through a point of tangency obviously is a tangent. Right? And this tangent will have a gradient. Now you see what happening here. Between 2, 4 and 1, 1, the gradient was 3. Between this point, 1.75, 3.0625, and 1, 1, the gradient is 2.75. Between this point, 1.5 and 2.25, the gradient is 2.5. Between this point, 1.25 and 1.25, 1.5625, and the point 1, the gradient is 2.5. Between this point, 1.05, 1.1025, and 1, the gradient is 2.1. Sorry, between this point, 1.1, 1.21, and 1, between this point 1.1 and 1.21 and the point 1, the gradient is 2.1. Between this point, 1.05, 1.1025, and 1, the gradient is 2.05. And we throw in another point 2, just to make the pattern even more obvious than it already is. Between the point 1.001 and 1.002001 and the point 1, the gradient is 2.001. Now, as I tell people all the time, observation is the first law of mathematics. Right? And we start from 6, gradient 6, gradient 5, gradient 4, gradient 3. And then from here to here, we move from gradient 3 to gradient 2.5, gradient 2.75, gradient 2.5, gradient 2.25, gradient 2.1, gradient 2.05, gradient 2.001. It appears that it's heading towards 2. It's getting progressively closer to 2 without actually reaching 2. So from 2.05 to 2.001, it stands to reason that if we insert another point between point 1.001, between this point and the point 1, that the gradient will get even closer to 2. 2.000001 or 2.000005 or something like that. So as you get closer and closer to the point 1, the gradient of the line segment gets closer and closer to 2. So in plain English, we can say, based on our observation, right? Observation is the first law of the jungle, and that is what I tell my students all the time. Based on observation, it appears that the gradient is trending towards 2. Now we use some modern language now. It's trending towards 2. Using social media language now. It's trending towards 2. It is approaching 2. It is moving towards 2. In the language of mathematics, we can say that the limit of the gradient of the line segment as the length of the line segment tends to 0 is actually equal to 2. So based on everything we have done so far, I want to believe I could draw off the curve now, you know. Yeah, I don't think I need the curve anymore because we're going to get abstract now. So we start with an actual curve that we could relate to from, well, we start with the straight line, and then we use an actual curve. And I'm going to use this same curve to demonstrate, in fact, that the limit is actually 2. The limit of the gradient. And then we're going to get general now. And that now will start to tell us what differentiation is. So in other words, and before I go, one last thing I want to mention here is that just as we discussed the gradient at a point in the case of the straight line, and we agreed that the gradient at that point was equal to the gradient of the entire line, or the gradient of any line segment, we also have the concept of the gradient of a point here. And just as we saw that as we shorten the line segment, the line actually approaches this tangent here. It means therefore that the gradient of the line segment whose length is 0, that is to say, the gradient at a point is equal to the gradient of the tangent. Because we established over here that the gradient of the chord was equal to the gradient of the secant line, because the chord was part of the secant line. So if the chord is part of the secant line, then the gradient of the chord must be equal to the gradient of the secant. Or in reverse, we can say that the gradient of the secant is the same as the gradient of the chord. Either way is the same thing. So as this chord gets to the point where the length of the chord is 0, that is over here, then whatever secant line is associated with that chord of length 0 will have the same gradient, whatever that gradient is. That gradient will be the gradient of the chord. And that secant line is what we refer to as the tangent. So therefore, at the limit, in the limiting case, so to speak, the gradient at a point being another way of saying gradient when the length of the line segment is 0, gradient when the length of the chord is 0. The chord that we progressively shortened approaching the point here. The gradient at a point is equal to the gradient of the tangent at that point. So, with the straight line, we have the concept of the gradient of the whole line. We have the concept of the gradient of our line segment on the line. And we have the concept of the gradient of a point on the line. And all of those are the same. Gradient of the whole line is equal to the gradient of the line segment is equal to the gradient at a point. Excuse. However, in the case of the curve, we established that each line segment has its own gradient, and as you shorten the length of the line segment by bringing one end closer and closer to a fixed end, you get to a point where you have the gradient at a particular singular point, and that gradient is equal to the gradient of the tangent. So in the case of the curve, the concept of the gradient of the entire curve doesn't exist. But we can have the average gradient between 2 points on the curve, which is equal to the gradient of the line segment joining those 2 points. just as we had in the case of the straight line. And just as we had in the case of the straight line, we also have the gradient at a point. So in the case of a curve, we talk about the gradient at a point. And that is the concept that is most commonly used in this thing that we refer to as differential calculus. All right? Yes, just as in the case of the straight line, we could have the gradient of different line segments. But unlike the case of the straight line, where all line segments have the same gradient, we established that in the case of the curve, every line segment has its own associated gradient. And similarly, just as in the case of, did I say just as just now? Okay, let me run that over again just to finish. Now, here's where I'll need the straight line, just as a matter of immediate contrast. All right? So I will rub off this tangent here. Right, so if we have a straight line, as we had on the left side here before we got rid of it, we established that the gradient of any line segment is equal to the same regardless of the length of the line segment, regardless of where the line segment occurs on the line. That is not the case for the curve. Each line segment has its own gradient. We also established, well, we also agreed that the gradient at any point on the curve is the same, regardless of where the point is. That is not the case for the curve. For the case of the curve, just as happens with the line segment, every single unique point has its own unique gradient attached to it. In other words, the gradient of the tangent at each point will be different to the gradient of the tangent at every other point on the curve. And that is one of the things that differentiates a curve from a straight line. Straight line, the gradient is the same no matter what. Curve, the gradients change as you move along the curve. And that gives rise to a whole branch of mathematics that we refer to as differential calculus. And of course, the concept and the concepts involved in differential calculus are used in a variety of other fields as well. That is something that you will discover as you go further into the maths. Good. So we're okay with that. Now, let us deal with the general issue, not the general issue, sorry, the specific issue of demonstrating that the limit of this gradient is actually equal to 2. All right? So we're going to do that in the next video. So stay tuned.